All right, so to start our conversation on vectors, we already defined vectors, but now we need to be a little more precise in that vectors are more than just numbers with directions. They are also dependent on direction, not in one dimension, but in two dimensions as well, and possibly even three dimensions. But for our purposes, we're just going to stick in two. So let's talk about vectors in two dimensions. Okay, so to start the conversation, let's look at a basic idea of a vector. So the first thing we're going to do, we've already discussed some things with vectors, right? So let's put the definition back. So a vector is, it's a number with magnitude and direction. Okay. Now before, magnitude was simply the number and direction was the positive or negative sign. But in 2D, we can't do that anymore. Okay, here's an example. If I have a grid, assuming that it's scaled appropriately, let's say we go on 4 units on the y-axis and we'll say 3 units on the x-axis. So these are standard axes. This isn't position or anything. Okay, I can have some sort of vector drawn from the origin that extends out to that point 3, 4. Okay, and it's a vector if I make it an arrow, because that says the direction of this vector is up and to the right. Okay, so the direction simply is the way it points. So the direction is the way it's pointing. The magnitude is actually the length of this vector. So however long the vector is, that tells us the magnitude of that vector. So that's one way. The way that we would typically write a vector, so before, we identified some different vectors. Right, we said things like a velocity number. So velocity is a vector, and speed was a scalar. So we're going to be a little more careful with how we write these now. Vectors, okay, are typically written as whatever the variable is. So we'll call it vector A, and it's given this little arrow on top. Okay, that implies that it's a vector. A scalar would be written as that vector with the absolute value symbols around it. So that would be scalar. All right. So in the case of velocity, you would have the vector v. And if we wanted to write speed, that would be the absolute value of the velocity. Okay, so this is some of the ways you're going to see us write those letters mathematically to signify whether or not they're vectors or scalars. But let's go back to the graphing of a vector really to start off this conversation. So if I were to have some vector in space, okay, and we'll call this vector A. Okay, if we wanted to define this vector, we can't define it unless we have some coordinate system. And so our typical coordinate systems, the ones we're used to, is when we have an x and a y axis, which means vector A consists of two components. Okay, there is a vertical component and there's a horizontal component. Now in the previous slide, these were defined by simply using the coordinate of the top of that vector. And it kind of works the same way. But the way we write this is if the vector is A, then the red line represents the y component of vector A, and the horizontal component represents the x component of vector A. So that means we can define the vector in an equation as the vector sum of its components. Okay, now the important thing is we can't do anything else with this. Okay, these don't combine. For example, so on that previous slide, we said the x component was, I know it's not drawn right here, but we said the x component was 3 and the y component was 4. So it doesn't mean that if I wanted to know the full magnitude vector, I wouldn't write, a vector is equal to 3 plus the y component, which is 4. I wouldn't write this and then just simply say that, oh, vector A is 7. Okay, that is definitely not true, because I can't add the 3 and 4 together. It's similar in a math class where you have the equation x plus y. Okay, this does not mean that the product is, or that the end result is xy. That's multiplication. Okay, there's nothing I can do with it. It's just stuck as x plus y because they're not the same things. Well, it's the same idea. These can't be added together because they're not like components, so they're stuck that way. Okay, so that's one of the ways when we write it out mathematically. So we need something to aid us in writing this out. So it defines something that we call unit vectors. Okay, and so a unit vector is simply a vector whose magnitude is 1. So a vector with a magnitude of 1. Okay, and what we use unit vectors for is to really specify a direction. So, for example, in our above equation, or in our above example rather, we said the x component of A was equal to 3. Okay, and so the unit vector that we use for this, okay, the positive x direction is given the unit vector. It's basically the letter I, lowercase, but with what we call a hat on it. Okay, so this would literally be read as I hat. And that symbol, it's not an arrow like the other vectors. This triangle represents that this is a unit vector, and all it represents is a label of direction. There's no magnitude to it except a value of 1, and so for that reason we just use it to label directions. So in other words, this x component for A, right, again, so you see it, the x component of A would simply be 3I hat. Magnitude is the 3, so that vector would have a length of 3, and the direction is in the positive x direction, because that's what I hat means. Okay, so it follows that if I hat is x direction, then we use the letter J to represent the y direction. And we won't use this right away, but we'll use it later on in the year, is the z direction, which would be a k hat. Okay, so those things represent what we call our unit vectors. So in our above example, that means we can now write this whole vector, a vector, okay, is the x component, which is 3 I hat plus 4 j hat. Now, unless the unit vectors match, we can't combine them. And that helps solve the problem we had with saying that 3 plus 4 is just 7. If we have these labels on them, you cannot combine them unless they have like labels. Okay, so that's what the ideas of unit vectors are. All right, now let's talk about how we add vectors, because that's probably the more applied area. So vector addition. Okay, so there's a couple ways. Let's talk about graphically. So say we have a grid, and these are again standard XY axes, these are not positions. Okay, and we have two vectors. Let's say we have vector A, points like this, and we have a vector B, which points like this. Okay, so if we wanted to add these vectors, so let's say we wanted to find a new vector, let's call it C, where C is a vector sum of A and B. Okay, so graphically, how do we do this? And the trick is, well, we take our vector A. So we just kind of look over here at vector A. And what we do is we redraw it at the head of vector B. So if it's perfectly scaled, you should draw A exactly as it would be. You just kind of pick it up and move it over to the head of B. And then you do the same thing with vector B. We're going to pick up vector B and we're going to move it at the head of A. Okay. Now, where these two parts, the two heads intersect, we basically start our vector C, the sum of these two vectors, at the same origin, and we draw it up until the head reaches that intersect point. And that would be our vector C. Okay, and that's it when it comes to, okay, that's all it takes to add vectors. So, if we wanted to do this in subtraction, so say we wanted to find a new vector, let's say vector D, where vector D is a difference between vectors. So we'll say A minus B. Okay, the first thing we have to identify is, what is subtraction, really? Well, subtraction is really the addition of vector A plus the negative of vector B. Okay, and so how would we draw a negative vector B? Well, I won't draw these perfectly, but assuming I'm using the same vectors, where this line represents A, okay, and this one represented B, the negative of B would be in the opposite direction. It'd have the same magnitude, but opposite in direction. So now, how do I add these vectors? Well, I redraw A, I redraw B, and I connect the dots. And that would be the difference between A and B. Okay, so graphically it's not a big issue, and for the most part we'll use graphical for more conceptual understanding of adding vectors. What's more important is, how do we add them mathematically? And adding them mathematically is not that difficult. So we did graphically, so now we're going to do algebraically. Okay, now, so we're going to write out our two vectors. We had vector A, which was something in the x direction, plus something in the y direction. And then we also have vector B, which is some amount in the x direction, and some amount, whoops, not A, and some amount in the y direction. Okay, so what do I get when I take, so a new vector, and we add together A and B? So A and vector B. Okay, and so vector C. Okay, so we know that vector C is going to have its own components, right? Some amount in the x direction and some amount in the y direction. So the question is, how do I find these two components? Okay, well, it's actually very straightforward. We mentioned before that I can't combine an x to a y, right? I can't take these two numbers and simply add them together because they're in different directions. What I can do is combine like terms between the two vectors, which means that the c component the x component for vector c is actually going to be the sum of the two x components of the other two vectors. The y component would be the same thing. It would be the sum of the two y components. And don't forget your unit vector labels. And that would be my vector c if I was adding it algebraically. Okay, so let's throw some numbers. So vector A we'll say is 3i hat and 4j hat. Vector B is, we'll say, negative 2i hat plus 2j hat. So what is vector C if I want to add A and B? Okay, so first I want to combine x components, and then I want to combine j components. So the two x components would be from A I get 3, and then from B I get a minus 2. For the y components, from A I get a positive 4, and from B I get a positive 2. So 3 minus 2 is just 1 I hat. 4 plus 2 is 6, and that's j hat. So there's my sum total of A and B. Okay. Now, one other thing to do with vectors. We mentioned before the magnitude of the vector. So let's say, we'll go back to that very first example we did, where vector A had units of 3i plus 4j hat. So if I graphed it out, it would be 3 units on the y and 4 units on the x. It would look something maybe like that. It's probably not perfect, but it'll work. So that is our vector, and it gives us everything we need. It gives us the magnitudes, and it gives us the directions. Okay, but what if I wanted to know just the one magnitude? In other words, what if I wanted to know the length of this vector? Well, if you notice, it makes a triangle shape. Value 3, value 4. So how do I find the full magnitude of the hypotenuse? Okay, so if you remember your geometry, trigonometry, you would know that the hypotenuse of this triangle is Pythagorean theorem. So the magnitude of vector A would be applying Pythagorean theorem to the two components. So the magnitude of vector A would be 5 units in this case. That's the magnitude. Now, how do I find the direction? Okay, so direction is typically given by an angle. Okay, so if I mark this, I'll do it in a different color. If I look, there's an angle here, right, called theta. That angle will tell me what direction to point a magnitude of 5 units, and that'll give me the full vector. So now how do I find that angle? Well, if you remember from trigonometry, okay, you worked with these trig functions, SOHCAHTOA, right? So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if I want to solve for this angle, what two pieces do I have? The 3 represents the adjacent to my triangle, and the 4 represents the opposite. So given that I have adjacent and opposite, I can use tangent. So the tangent of this angle is opposite over adjacent, where the opposite side is 4 and the adjacent side is 3. So if I solve this for the angle, we'll have to do the inverse tangent of 4 over 3, and that'll get us right around 53 degrees. So that means vector A can be written one of two ways. I can either write it as it's 3i hat plus 4j hat, magnitudes and directions, or I can say that the magnitude of A is 5 at 53 degrees above the positive x-axis. Okay, now that label is important because you'll notice when we graph this vector, where is the 53 degrees measured to? It means it's starting from the positive x-axis, right? Positive side of the x-axis, and it's going above that axis to create 53 degrees. And that's how we would write out a full vector using magnitude and direction notation. Now, it's going to be a lot easier if you keep it in unit form to do your work, but typically at the end of the problem, it wants to know what is the final magnitude of the vector, and it wants to know what is the final direction of the vector. So your answers are going to want to be in that form. But typically, to solve the problem out, you want to use the unit vector form because that's going to help make your math steps much, much easier. All right, so the last thing I want to do is a little bit of review using SOHCAHTOA. What if I gave you a vector? So let's say you've got a coordinate system of x and y, and I gave you a vector. Say it's 10 units in magnitude, and it's moving at, or it's in a direction of, say, 30 degrees. Okay. What would be this vector? So say that 10 units is the magnitude of vector b, just randomly. What is the vector in unit vector notation? So right now I've given it to you in the way we solved in the last example. I gave you the magnitude was 10 and the direction was 30 degrees north of the x-axis. So what if now I want you to tell me what vector b is in unit vector notation? So how do I find the x component? Let's start there. So you got two components, x and y, a horizontal and a vertical. So let's start with the x. How do I find the x component? Well, again, if we look at the triangle, you have a hypotenuse, you have adjacent side, and you have an opposite side. So what two pieces do we have? We have the hypotenuse and we have the angle. And we're trying to get the adjacent. So which trig function can I use, okay, from SOHCAHTOA? What can I use to find the adjacent side? And given that we know the hypotenuse and we're trying to find adjacent, we'll probably use cosine. So the cosine of 30 degrees is equal to adjacent over hypotenuse. The adjacent is our x component for b, and the hypotenuse is 10 units. So if I'm going to solve this for the x component, I will multiply the 10 over. So that's 10 cosine of 30. So you should get an x component of around 8.6 units. What if we wanted to find the y component? So for the y component, we want to try and stick with the same, well, rather, we don't want to use tangent. Tangent's good for finding the angles. So if we can avoid using that to find the x or y components, that would be great. Save tangent for finding angles. So since we have opposite and hypotenuse and the angle now, we should probably use sine. So in this case, the sine of 30 is opposite over hypotenuse. So that's the y component of b over 10 units. So if we're going to solve for by, we're going to do 10 times the sine of 30, which will give you 5 units. So that means our vector in unit form would be 8.6 I hat plus 5 j hat.